Okay, so who is gonna follow along?
Okay, remember what we need to be able to follow them.
You need to have downloaded the Oracle VirtualBox software, and then also download the Prism tools from the Prism website.
VirtualBox, is that just like a VM or is that?
Yeah, Oracle VirtualBox. Yeah. But this is going to be an interesting presentation because I think so I'm going to present codes from PRISMS, which is a software project in the mechanical engineering and material science departments. And unless I really mess something up, I think I found a bug in their continuum plasticity code. So we can just that's all we're going to look at for that one. And then I'm going to talk a little bit about my own research, and y'all won't follow along. So I would say the demo part is somewhat tentative, but you know, you can play around if you like. And seems like we have a lot of time since we went through the elections quickly, so I can give you some help. Okay, so what we're talking about is solving computational elastoplastic problems. So many of you are probably familiar with the concept of like Cauchy stressed and elastic bodies, but I'll just say a little bit about it. Okay, great, we have Chaitali here. I'm going to introduce her later, and maybe she can even tell me about this bug I'm struggling with. Let's see. So, you know, essentially, like, what do we do in engineering mechanics and engineering solid mechanics? We have some body, like an aluminum part in a plane, or, you know, something in your car frame, something that you want to see what are the internal forces in it when that thing gets bent in service, or pulled on or pushed or whatever. And so at every material point, you think of this, you know, infinitesimal cube, and what are the forces acting on each face of this cube, and in what direction are they after? So we define this thing called the stress at this point, kind of what at this material point and the material point next to it, what is it pulling on it, pushing on it, kind of this thing. This is the concept of internal forces. You basically have some traction, some force on any of these surfaces, and the stress at some point is the limit of that traction over some area. You take it to the limit, take it to an infinitesimal point. So this is the concept of you know, elastic stress. So when we have some engineering part, you know, you won't have some experiment, you're pulling on your material, you're doing something to it. In our computational model, we take that whole body, we discretize it into a bunch of different cells, and then on this computational rendering of that elastic body, we apply some boundary conditions. And that just means, how am I going to move this thing to try to replicate what happened in my experiment and then solve the governing equations of the system to have, you know, some virtual representation of the mechanics. But there's one central part to this problem, which is that if I'm going to take this mesh and I'm going to distort it, what defines the relationship between the displacements and these internal forces that are generated in that elastic body? And that is what we call material properties or constitutive laws. And in this case, we're going to focus on these elastic bodies that have some elastic, that means reversible, it'll snap back once I remove my distortion, and some plastic permanent part that when I pull it is, in some sense, in some extent, it will stay deformed. Elastoplastic. So that's what we're doing. So there are two approaches to these type of problems generally, continuum plasticity or crystal plasticity. Continuum plasticity is the kind of thing you probably would encounter, you know, if you have used Abacus to do some plasticity problem. We are zooming out to the large scale of the material and not considering any details about microstructure, about grains, about these kind of things. We just kind of say this is some homogeneous, macroscopically homogeneous and perhaps anisotropic material. And you define these constitutive laws by doing a bunch of experiments in the lab and typically more phenomenological approaches. But of course, you can try to build in some physical theories as well. Crystal plasticity goes way, way down in length scale. Not quite to the atomic level, but more these grain and microstructure level features. You know, you use some theories of the physics at these length scales, the dislocations in the material, the crystal planes slipping relative to each other. And if you ever heard about twinning, you also do twinning. If you want to know more about twinning, you can ask me after. This is also my research topic, and I will say something a little bit about it in the second demonstration. So crystal plasticity is of course crucial when there are things happening at that length scale that you care about and perhaps affect the performance of your part. So what are the examples I put? Yeah, some electronic devices. Oh, and I put turbine blades. You know, when you're thinking about like fatigue and stuff like that, then there are things at the grain level that maybe you want to simulate. So, you know, it's used also, let's say, like in material design, you know, we want to look specifically at things changing composition and things like that. If you can characterize those things, you run crystal plasticity models to try to learn things about what's happening at very fine length scales. And these are both available in the PRISMS code that is developed as UMISH, like I said. And the link is here. Slides will be added to the GitHub, you know, when I get to it. Okay, so we will perhaps look at this example, but maybe another one. So let me, who said they were gonna follow along? Okay, that's right. So yeah, if you have the PRISMS code loaded up, hold on, I'm gonna unplug this a sec so you guys don't see my Discord. I'll just go over to my terminal window. Okay, so maybe first let me introduce Chaitali. Chaitali is a postdoc in the PRISMS department. She is at the back there. And as I understand, would be the main contact for plasticity type things, perhaps. So I'm gonna put Chaitali on the spot because I tried running the canned example in the continuum plasticity codes. And this is a simple tension problem. Why is it looking like that? One second. Okay, I don't know why it looks like that, but we'll go with it. Everyone can see. So this mesh has some elastic and plastic constants imbued to the material properties. And we're pulling like this. And I was quite surprised to see this result. Like the stress is quite heterogeneous. We wouldn't expect that. And Chaitali, I don't know what you think, because I tried many different things. I tried decreasing the element size. I tried taking very, very small time steps, and my residuals just plateau. No matter what I do, I tried like 64 nonlinear increments, and it's still level off. So I'm hesitant to say, but I think there may be some bug in the continuum plasticity codes. I don't know.
I think we had to look into that a bit more,
Yes.
just to see that much heterogeneity. But have you seen like increase the size along that so that you don't have any size effects?
Make it longer. Make this thing. Yeah, we can try. Let's try it now.
Yeah.
So this may be interesting. I will show you guys, you know, how I try to address this issue. Okay. Okay, so how do these how do these PRISMS codes work? Basically, you have some input file, like in Abacus, you would have .imp file. We have this .prm file, and you also will define some other text files that it will read things from. And so here in this file, in some encoded way, I've defined this simple tension boundary condition that I'm going to fix a certain phase and I'm going to move a certain phase. That's all that's in that text file. PRM file, I'm going to open it right now. So PRM file defines many things. First, what is the order of your finite element? What's your order of quadrature? These things typically never change, so just leave them. Number of dimensions, we are going to do 3D all the time probably. And here's the size of the domain in different directions. So I think Chaitali's recommendation is I'm going to make the X bigger.
Let's see. Yeah. What was like in the BCs, how much deformation?
Huh?
Tension BC, like how much deformation are you giving for the displacement?
How much displacement? I think it's like 0.05. Yeah, I think it should be big enough. Yeah. Anyway, you know, if I wanted to make that dimension bigger, maybe I will do something like that. Change it to 10. Then you in this block, you're defining your mesh parameters. So initially, I'm gonna like divide it in the X direction in 5 places, and in the Y and Z direction just once. And then you can set this refine factor. How many times do I subdivide all of those elements again to make a finer mesh? And typically you want to put these divisions to, how can I say, their most reduced form, right? Like if this was 10-2-2, I would change it to 5-1-1. And you want to use these refine factors to get the mesh density that you want. This has certain implications for multi-threading when you send your problem to be solved off by the computing cluster. Then I will skip some things. This is defining which outputs you want to give and how so. Again, like I said, you need to give it the text file that you have defined your boundary conditions in, and some solver parameters, what step size you want to take, total time, and different convergence things. And here you define your elastic parameters. So you may or may not know what Lamé constants are, but if you know like Young's modulus, shear modulus, these things are all calculated from some equations like that. And then our plastic behavior, yield stress, at what stress will it not stop being elastic and move on to plastic behavior? And then some different hardening exponents. Let me say, like, for Samsung, what strain hardening is. So we have an elastic plastic material. So on this x-axis, we write strain, which is like change of length over initial length in some direction. Better pen.
To be equilibrium.
Yeah, before you start to deform it. So 10 there, and then it'll be longer than 10 when I stretch it. And then this sigma is like this force over area thing that we consider as a measure of the internal, energy that's being put into the material. Again, cut in some dimension. So when we talk about elastic behavior, there's a linear relationship typically. And if I brought it to this strain level and then I released it, it will go back. It'll dissipate all its internal energy and come back to this state. Then we go to plastic. So there's this sigma y, the yield stress that's defined here. Then it's going to start to do something nonlinear. And there's many different models for this nonlinear behavior, but one model, linear hardening model, this strain hardening exponent, washing over a lot of things, but generally just characterizes how this nonlinear behavior forms. And you call it strain hardening basically because this slope is getting stiffer progressively. So the material is getting harder to deform. And kinematic hardening is something else. If I pull it in this direction, and then I want to then bring it back and maybe compress it, the amount of plasticity that's accumulated when you pull it will have some effect on its behavior when you compress it, because the material has gone under some of this permanent deformation. That's called kinematic. Last couple things are just a couple algorithmic details, so I'll skip that. If you are on Great Lakes, you run your models using this shell script. We'll have I'm sure a workshop about Great Lakes sometime in the future, but you know, conceptually, basically, there's a main file in this PRISMS codes for the continuum plasticity model, and you reference your input file, send it off to the supercomputer. If you want to run it on the PRISMS virtual box, can't remember the command exactly, but if you Google GitHub plasticity PRISMS did I say GitHub already? Yeah, Google that and then you'll find the command. Yeah. Okay, sure. So, Jacob, you want to take this one? I'm just kidding. So, strain hardening is about this, you know, this evolution in kind of stiffening of the material as you get more plastic deformation. Kinematic hardening is like, say this is the positive and this is negative. So if I loaded it and then it had some plasticity, here is sigma y and here is minus sigma y. When I come down, before it reaches the negative of this sigma y, it is going to start going plastic. And how much that happens, that's called kinematic hardening. So kinematic hardening is going to be really important if you have some cyclic problem where the part is going into tension and then compression over and over again. Or say you have a wire that you're bending like this and this. One side is going to be in compression and tension, and then the reverse, you go back and forth. And you need kinematic hardening to one of these kind of things. So just to illustrate this, so I had my terminal open already. This is what I was talking about, and I'm going to show you guys how to look at this output, at least in the on Great Lakes. And if you run it on the PRISMS toolbox, it'll just print this out to your terminal as well. But here I'm doing like 16 nonlinear iterations, and my residual is kind of like plateaued. It's not going down anymore. I don't think anyone in this room knows what's the reason for that. So here I have some log output file from the last time I run it. So I'm going to remove that. Well, let me switch this over first. Just for people on Zoom so they can see what I'm doing. And then you submit your shell script with this command sbatch, and then reference your shell script. Press enter. And in a minute, once the cluster has received my request to run this problem, it's gonna send me this out file again, and we'll see okay, so let's do. So I like this command tail -f, I mean refresh or something like that. And I put this log file, so every time a new line is printed, it's going to update to my terminal. I can see what's going on. So you can see here's the first couple lines printed. This is how many CPUs I use. So I'm using 36 CPUs. The number of elements in my mesh, the number of degrees of freedom in my mesh, and telling me that I'm starting to run the model. So in a second, it'll start printing out some details about the convergence of this model as it's running. And
Sorry, is this running locally or is this on Great
on
Lakes?
Great Lakes, yeah. Yeah, if you download the PRISMS toolbox, let me do this while we're waiting for that to print some stuff for us. Yeah, why not? Because this is how you will learn the plasticity code. If you want to plasticity. So this is the GitHub. And there's a little instruction here about installing the code and how to compile it and stuff like that. Yeah, so Vitaly, if they want to run it on the Prisms code, you just use kind of this part, right? Without the MPI man.
No, you can use the MPI. Or if they have like in CPU some of
Do they have
the
MPI on the Prism toolbox?
do like MPI run 4, 6.
Okay, yeah, so
You won't get like a 32, but they can get.
yeah. So yeah, you can use this whole command, just np maybe. It depends how many CPUs you made active to your virtual box when you install it, but 4 or 6 or 8 or something like that for this nprox. And then yeah, you'll also be running it in parallel. Okay, so now the model is running, and it's using some sort of Newton-Raphson method to solve this discretized PDE. And so here we are at the first increment, and it's done one nonlinear iteration, and there's a very big residual, so we better do some more. And yeah, it's a big. I refined the mesh a lot, so it will take a while. Yeah.
Are these steady problems or transient problems?
These are steady state, yeah.
Can the code do transient or
I would say for continuum plasticity, I don't think it's implemented yet, although I'm not totally sure. Yeah. Yeah. Any other questions? Okay, yeah, sometimes it helps to just tail again. But yeah, here you can see the residual went down a little bit. So ideally it should go down to some very low number like e to the minus 10 or something like that. But right now I'm seeing that it doesn't go down past e to the minus 4. So I really don't know why that is. If you want to help me find that bug, join the club. Huh?
Let's see your input file afterwards.
Yeah, and Chaitali is gonna check it out as well, yeah. Okay, so let's change gears now. Get back to the slides. Okay, so I'm going to talk about my research topic a little bit, and you guys are going to see some results even before my PI saw it. So I have a group mate who is doing these experiments on copper, aluminum, nickel shape memory alloys. And we have this X-ray diffraction experiment that we did. We shoot this X-ray, we shoot our sample with some high energy X-ray, and then the reflections that come off of it, you can see kind of the morphology of different phases inside the material. So this is one grain, and there is one crystal phase that shines up very brightly and one that is totally dark. You can see in some orientations, like right now, see these bands going across. So that is another crystal phase that the material is sort of shearing, and it is doing this to accommodate the strain imposed on the material. And there's a lot of questions about where and with what shape these things will form. And in my research group, we try to answer these questions by doing these in situ experiments, loading or heating the material I just went to Cornell last month to do some experiment where we have actually a single crystal of these shape memory alloys. And we pulled on it and we also heated it to different temperatures. So we try to investigate this behavior thermodynamically. One question is that this second phase, these dark bands, they have different what we call variants that they may form inside the parent grain. And you can think of it like this: if your parent phase is cubic, and say this other phase is orthorhombic, so just one side is changing in length, there's sort of different symmetry related orientations that it might take. And which one was it? You can't tell anything from this because it's black. We can't. So we have to come up with some theory to predict which phase is it going to be. And that's part of my research activities this semester was I took the whole grain map and using the PRISMS plasticity, the crystal plasticity module, I made this finite element model and I see what the stresses are in between the grains. And we know that in between the grains, there's going to be some stress concentrations. And from our theory in this field, we know that it's likely that that is the place that these bands are going to originate. And you can kind of almost see it in this GIF because we are looking at just one grain now. But when you see these bands, it's kind of related to this corner here where it's touching a bunch of other grains. They all emanate from that point. So what is different about the crystal plasticity module compared to the continuum plasticity module? Well, I can define different regions in the mesh associated with different grains, and I give those regions a certain orientation. So now we are modeling the anisotropy of the material at the grain scale. And that is why we are able to, reproduce what we think is happening in the mechanics of this material. And let me open ParaView again. Let me see if I Yeah, I don't know why ParaView is looking like this when I plug in my laptop, but anyway. So first I can color this by the different grain IDs so you can see how I've split this mesh up into different grains, and all these different grains have a different orientation, so their elastic properties will be oriented in a particular way. Let's look at maybe the von Mises equivalent stress. So here you can see, let me hide the edges. Here you can really see along this grain boundary, the stress is having some concentration. And I prepared one other thing, but I can't find the file I saved for it. Let me maybe. Okay, so here I'll look at just one grain, the big grain. And now we can see sort of inside the material. And at this point where all three of those grains are meeting, there's a high stress concentration. And so from this, we have sort of validated that those things that we saw in the experiment emanating from this grain triple junction, it is due to some stress concentration there. I'll show you guys one more thing. So one thing you can do, if someone's really interested, I can dig through my files and show you how to do this, but you can make some Python scripts also in ParaView that takes all these things that we output, the stress state, and processes them in some way, and then immediately show it on the mesh. So when we have these different variants, like who has studied like plastic slip, like crystals slip, something, yeah.
Steady.
Sure, but you know that to determine which crystal system is slipped, you calculate something like Schmidt factor, these type of things. For these variants, there's something analogous. So what I would put in this script is I would take all components of my stress vector and say, okay, I want to see which variant is most likely to form in this grain with this stress state. I'll calculate that results shear stress and then plot it. And I did for the variant that we expect to be in that grain, and this boom, huge stress concentration right where the variant is right where we saw those phases actually appear in our material. So yeah, apologies. I had made a lot of effort to save the whole session of this ParaView so I could show you guys that cool feature, but I just can't find it right now. Okay, let me wrap up.
GitHub.
Sorry?
You have that on a GitHub afterwards?
I will upload it on the GitHub, on our SC2 GitHub, yeah. When I get home, I'll find it and put it up there, yeah. Yes. Yes, you know, after this, there'll be more stuff on the GitHub and you can look through it. Yeah, what's up?
Are we trying to find only with a single crystal or in polycrystals? Because the way, if it is with the multiple grains
Yeah.
are here, maybe we need at least 5 slip systems to activate if we need to deform a grain. So are we looking at that too? Or-
Yes, so these twins are something different from slip systems. But if you have any questions about how these things are handled in the crystal plasticity code, those different plastic slips, you can email Chaitali or ask anyone in PRISMS. They'll be much more knowledgeable. And the last slide here, I'm going to show you the different resources to learn about this PRISMS plasticity model. But yes, certainly it's prepared for polycrystal problems. That's what this whole code is for, to have a mesh with multiple grains in it and simulate the grain interaction. Okay, so how do you learn about this code? Go to the GitHub and let me open it. Okay, and yeah, that link, I brought you guys straight to the training materials. So every 2 years, I believe, PRISMS does this symposium on campus and also runs training for the PRISMS code. So it just happened this fall, so it'll be next fall, they'll have it. And all those slides are in the GitHub that you can look over the basic things you need to learn about how to use this code. There's also the PRISMS Plasticity YouTube channel. So I guess those sessions that happened during COVID, they uploaded to their YouTube channel. And here you can see like PRISMS Plasticity session 1, session 2 from 2022. There's also the website where you can see how to download the code and install it and run it in different ways, and some more science things beyond plasticity that are going on in this code base. It's all up there. And Chaitali's email is here. She's very helpful. She helped me with different issues that I ran into the code for my research and otherwise. And last point, I believe, and we haven't talked about it much in the board, but we would like to get Great Lakes access for our club members. So Great Lakes is the campus-wide computing cluster. And I use it right now because my supervisor pays for my account. We would like to give access for y'all for these workshops and for working on projects because yeah, that PRISMS VirtualBox is good to try out and learn how to use the code, but to run serious problems in a reasonable amount of time, it's best to use Great Lakes. Okay, thanks a lot. Any questions? Yeah.
You give a sense of like what equations govern like the behavior at the like the continuum, but like crystalline level? Like what equations do you solve?
For crystal plasticity,
Yeah.
I'll have to be very vague, but sure. Or actually, no, I should just show you guys the PRISMS documentation. Even better.
So I started like, I need like a right initial function, it basically just does like the 10 executes. Like in our. Like if I compile to regular. Maybe that's. Yes, I think this is essentially you're right.
So the basic idea of crystal plasticity is that you have this thing called the deformation gradient. And what the deformation gradient is so say I have some 1D material that exists on this bounds between 0 and little x. Then I stretch it, and now it's from 0 to this big X. We call this the reference configuration, and we call this the deformed configuration. The deformation gradient is the derivative of these coordinates in the reference configuration with respect to the deformed configuration. So some measure of like stretching between these two different states of the material. And as I said previously, these elastoplastic materials have an elastic part and a plastic part. And this S is Schmidt tensor? Yeah, Schmidt tensor. So basically this crystal materials have different planes that might shift relative to each other. That's what we call plasticity. Subplane, dislocation, motion, and all these things. Essentially, we define all these sets, and they have some, thermodynamic conditions for whether they'll slip or not, the rate at which they'll slip, and we calculate those things, and we put them into this LP, which is some projection of this, stretching. It solves all these things, and then you accumulate all your deformations in addition to your elastic deformations. You do that at every time step. You track the state of all these slip systems at every material point in the mesh. That's it, basically.